In this topic of discussion, we are going to see about image transforms. Many times, image processing tasks can be best performed in a domain other than the spatial domain. So here, first we want to know about the spatial domain and the transformed domain. First, the pixels where we could able to process using directly is called spatial domain. Before changing the pixel values to any other value, if we access the pixels directly and we use it without changing the values, it is called spatial domain. If we want to convert the spatial domain into transform domain, which means that any other values or any other application of changing in the values or any other things based upon the requirement, we have to follow the image transforms. In this diagram, we could see the spatial domain values mentioned as f of x comma y, which means it has two dimensions x and y, and the transform. Any transform we can apply. We will be seeing it later. And then comes the operation. Any operation based upon the transform we choose. Then to get back the original image, we have to do the inverse transform. Then that image is called as g of x comma y, which means that the original image f of x comma y has been transformed into g of x comma y by applying the transform. Any transformation has to be follow forward and reverse transformation at the same time. Next, we have a question. Why we use transforms? In order to enhance the image quality like contrast, sharpness, we go for image transforms. And also to extract the important features like edges, textures, to reduce the noise for better clarity, to compress the images for saving the memory, and also to improve the computational efficiency in image processing. We go for transforms. In the earlier lectures, we have already seen about some basics of image processing. Now we will develop a system that whose input would be an image, output would be an image too, and the system would perform some processing on the input images. That is, its output as a processed image. So, as a diagrammatic view, if we explain the what is meant by transform, any 3D image around us will be converted using a camera and then sent to the image processing system. Then it gives an output as a processed image. So here the image is been cropped and the size would have been reduced. So any transformation will be applied inside and it has been enhanced to a better quality using any image transformation applied in the image processing system. So what are all the types of image transforms? Fourier transform, wavelet transform, discrete cosine transform. So we have given also the examples. It can be used for any compression types like JPEG, and also it is used for converting image blocks into frequency coefficients. Then half transform, radon transform, PCA, histogram equalization. Half transform is mainly used for edge reduction and radon transform is used for medical imaging, and principal component analysis is for used for feature extraction and compression, mainly used in face recognition algorithms. Histogram equalization is been used in medical imaging and satellite imagery. It is one among the non-linear transform. So in general, all the transformation has to be demonstrated as forward and reverse transform. So in general, the variables will be for mentioned for a transformed domain will be in the form of t of u comma v. Y we given as two summation terms is one for x and one for y, and then f of x comma y is the original image. Here r of x comma y comma u comma v is the term. It is called as basis or kernel, and which is the parameter used for transforming. So where u is equal to 0 comma 1 to m minus 1, v is varying from 0 to n minus 1. So same way the inverse transformation will take the form like f of x comma y, that is the original image what we want to recover. Then the t of u comma v will be the transformation which is going to be applied, that is the inverse is going to be applied for it. Now the same u comma v, the ranges from 0 to m minus 1 and n minus 1 respectively. And now comes the inverse transformation kernel called s of x comma y comma u comma v. Here is the example for a transformation domain DFT, discrete Fourier transform for a single dimensional signal. So here f of u comma v equal to x varies from 0 to n minus 1 f of x e power minus j 2 pi ux by capital N. So here u varies from 0 to n minus 1. So here now u acts as an index, which means that u1, u2, u3 like that it will be varying for every value. Here e power minus j2 pi is called as the kernel. That is, it varies from for every term. E power minus j2 pi is nothing but a Euler's formula says that cos 2 pi minus j sin 2 pi. Same way, inverse DFT. So it involves the original signal can be recovered using the transformed value called f of u. Here the kernel will be in a positive way, e power j 2 pi ux by n. Here some of the DFT properties are shown. It has the property called separability, periodicity, symmetry, translation and rotation. Separability means here we could see that if f of x comma y is equal to f of x into f of y, which means that the star represents convolution symbol. In time domain, if f of x comma y is the value for f of x star f of y, then same transformed domain also will be have the capital F of u star f of v, the same property. Periodicity. Periodicity in the sense if a time domain value is varied with a value called some capital M or N, same will be varied with the transformed domain also. If the 2D signal is periodic, its DFT has a sharp peak at discrete frequencies. Symmetry. Suppose if we have the real input with symmetric values, the same DFT will also have the symmetric magnitudes. Translation. Suppose a shift has been occurred in the time domain, same shift will be applied in the DFT also. Suppose any rotational, that is the spatial rotation, any circular shift with a 90-degree, 180-degree is happening in the time domain, same shift will be happening in the transformed domain also. Next comes the DCT, discrete cosine transform. The basis function of DCT are real because DFT had complex basis functions, but here DCT have a real value. DCT has very good energy compaction properties. DCT can be expressed in terms of DFT also. Therefore, fast Fourier transform called FFT implementation can be used. In the case of block-based image compression like JPEG, DCT produces less artifacts along the boundaries. This slide shows the discrete cosine transform values for a one-dimensional transform. F of k equal to summation n vary from 0 to n minus 1 f of n alpha of k cos of 2n plus 1 k pi by 2n. Here the kernel represents the cos term. Here k vary from 0 to n minus 1 and alpha k varies from root of 1 by n for k is equal to 0 alone and root of 2 by n for k is equal to 1 to 3 etc. n minus 1. Same way, if I want to calculate inverse DCT, the kernel term is changed to 2n plus 1 k by 2n as it is. Here, inside the summation, f of n is changed to capital F of k. For a 2D DCT, same terms are represented. Here, instead of alpha of k, alpha L is also multiplied and f of m, instead of that we have f of m comma n. Here the same way two kernels with m and n are used respectively. Here is the equation. We can see the comparison of DCT and DFT. Any n-point DCT of x of n can be obtained from 2n-point DFT of symmetrically extended x of n. So that is the equation given. Symmetric extension of x of n is given. And then DFT of x of n for a one-dimensional value. Same way DCT of x of n is written. Now by comparing these two equations, we arrive that capital Xc of k is equal to alpha of k by 2 e power minus j pi k by 2n x f of k. That is the final expression we get after relating both. Now, this is the output we get for applying DCT and DFT in any image. For example, DCT, we could see that the energy concentration is mostly concentrated at the corner. And for the DFT, the energy concentration is mostly at the center part of the image. The corresponding histogram is given. Here, the blue color line shows that the energy concentration at the corners, which means that the corner part of the image have the higher blue values, which means that higher pixel values are concentrated at the edges. And here, the values will be 0 till the remaining part. And the same way from 100 to 150, most of the energy are concentrated in the DFT values. So finally, we could see the summary of DFT and DCT. Their main application are image compression, image analysis, image filtering. And application in audio is audio spectrum analysis, modulation analysis. For DCT, it has a compression, MP3, feature extraction analysis. The formula is been given and explanation of variables is also given correspondingly. Thank you.